This is that video that everyone is going to love, and I hope this is going to answer a lot of questions about measurements and ratings. So we'll now look at the power rating. What does it mean? So when you read that an amplifier is rated for 50 watts or another is rated for 10 watts or 200 watts, what does that really tell you? Does it say you are going to have like bigger impact, slam, bass, dynamics, transparency, detail level if you go for a higher power rating amplifier? And my short answer right now is that all of these that I just told about you, from impact through dynamics to transparency, they are not defined by the watt rating. So it's not the amount of specified watts that will tell you whether your amplifier is capable to achieve any of this at a higher level. So what does the power rating specify if it doesn't specify any of these? And why not? And what defines all of these factors? I will tell about that in a future video. Right now, let's go through what power rating is, how it is calculated, and what it is good for. So the watt specification basically tell us how loud can your amplifier go with the dumbest signal possible. So what they do is that they give your amplifier, when they establish the power rating, is that they put on a sine wave. So basically you have a signal that's what I say, because it's the dumbest signal. When you listen to music, it's never a sine wave. So it's kind of like thinking like, okay, so who is the guy in school who can solve the equation 1 + 1 = 2, and who can solve the most of that in a single time? That kind of gives you the wattage rating. Now, and then you expect that that person who can write down 1 + 1 = 2 the greatest number of times in 1 hour, he is the best mathematician. But no, just give someone like a differential equation. Okay, can you solve the differential equation? No, that shows that you are a good mathematician. But how fast you can write down 1 + 1 = 2 tells almost nothing about your capabilities of higher mathematics. And the same is true for amplification. Just telling how big a signal can be just tells you how loud it will cap out. So when it will start to keel over, that is what it's telling you. And let's see how this thing works. So here we have like a nice figure, and when you see on the x-axis, that's the input signal. So when we are increasing the input signal, on the y-axis, that's the power output. So the more you increase the input, the greater power you get. And as you see, I'm going to draw with red. So up to here, it works really beautifully, because if you double the input signal, you get double the power. And that goes on until the amplifier is in its comfort range. But when you start leaving that comfort range, when you are starting to deplete the power supply reserves, when you are reaching the top range of the linear range of your amplification stage, any of the stages within your amplifier, then what you start to see, that even though you are increasing the input signal, but the power output is not exactly increasing as much. It starts to lag. So you see here, we have this starts to fall lower than what we are expecting here. No, I cannot draw very straight lines, but we are expecting a nice upwards curve, and we are falling off. And the difference between these two here, that what we expect to see and what we actually get, that difference will show up as harmonic distortion. So harmonic distortion is a result that you are trying to push too much signal out, and you cannot handle it, and your signal starts to collapse, and as it collapses it starts to widen, and this widening, that's the harmonic distortion. And let's look how this thing happens. So you see this purple signal, that's the sine wave, and when you want to increase it, it gets bigger and bigger and bigger, but after a certain point it's like something is pushing the top of the signal in, so it will starts to get shallower and fatter, and after a while it will start to develop ripples on the top, so it will look like this, like that thing. And those things, those rippling things, those are the harmonic distortions. So here you see with these down here and the other one, so these are like extra higher harmonic distortion, like third harmonic distortion, second harmonic distortion. And when you get these lower harmonic distortions, then it will start to look like this flattening. So let me just draw it here. So if this is the original signal, then it will look more like we start to turn into a square wave. But what we have here in the drawing, this is like tremendously high distortion added to the sound. So when you have this distortion and your sine wave almost becomes a square wave, of course with ripples here, that's already like gross clipping and gross distortion. That's when your amp sounds like something dying, and usually long before that we do not push our gear to reach that stage. That's really well past the audiophile region, but people, when they have their things at home, you know, kids with a boombox, yeah, this is what you get, that sort of gross, nasty distortion. In an audiophile gear, the distortion that is added, which is here, these little sine waves, are like 10 times or 100 times smaller than the ones here. So it's just a really, really tiny bit. And when you have a sine wave, it's just a tiny bit of widening. Really, if you look it on the oscilloscope, you can barely see the change from a pure sine wave. If with like 1% THD added to it, order harmonic distortion, it's barely visible. And actually, now I'm going to tell you something, that what is a fundamental difference between tube and solid state amplifiers is that for tube amplifiers you predominantly have second and third order harmonic distortion added to the sound. So it means that you have your sine wave, and that is going to transform more into a square wave. And eventually it never get to a square wave, because this would be truly massive gross distortion. However, what will be is that your sine wave, which is like a perfect wave, it will be tiny bit wider than it is. So here I have the top ear example. When you have the small signal, no distortion, you have a nice little top ear, and when you increase the signal, then you have a medium top ear, and when you increase the signal to the level that's beyond your amplifier's handling capacity, then your top ear starts to fatten. You see? Now he's like fatter and wider than it should have been before. So it's like a man growing, and when you reach your your 30s, then you do not grow anymore in height, but your belly starts to grow. So that's the effect you have with tube amplifiers when you push them too hard. The average overall envelope of the sound, character of the sound doesn't change, it just gets a little fatter. But the same thing happens all across the frequency range. So there is no difference between low frequency treatment, high frequency, mid-range. Everything follows the same route. And because second and third order harmonic distortion is already in your music, it's part of the music. If it's homogeneous throughout your range, it does not disrupt the character. It doesn't change the music content in such a way. However, it can have one big effect, and the big effect is that it will be impacting what kind of speakers will work with your amplifier. Because just imagine that when you have a nice sine wave, let's just try. Let's just maybe clean this thing here, so I can have a little drawing board here. So you have a nice sine wave. So it means that, and let's say this is a bass note, and we are talking about bass because that's the hardest region to reproduce for any amplifier. And it's because there you need to get the biggest cone movements, and there the cone is not coupling to the air of the room perfectly, so you have tremendous issues there. And also for tube amplifiers in the bass, that's where your output transformers inductance starts to become limiting. So you really need speakers that can play together with your amp. Which means that when you have your sine wave coming, then the speaker cone has to be able to go through this swift change. So when it goes out and it comes in, and it has to be able to move between the 2 points freely and without hindrance. And the only speaker cones that can do that relatively free cone movement in the low frequencies are high efficiency speakers, because they are high efficiency because the cone movement is not hindered by tremendous back pressure in a small tiny cabinet. So if you have like an acoustic suspension speaker, it means that the cone is really restricted from movement. It's not allowed to freely accelerate like a bullet. It has to be moved out with tremendous energy. So you need a transistor amp that has like a really high power factor and really high damping factor. And in that case, you have your bass down. But if you have a tube amplifier, then you need the ability to say that if the amp accelerates the cone, that cone accelerates like a bullet. And those speakers now that we have optimized to match our solid state gear, there the cones don't accelerate. They can move a lot, yeah. We have just tremendous cone excursion drivers, like 40 millimeter cone excursion is not unheard of for woofers. But the speed at which they can come out and go back is like a slug chug compared to what we have in high efficiency speakers mating with tube amplifiers. And that's really critical, because when you add a second, like a third harmonic distortion, and your wave starts to become a little bit fatter, it means that the slope at which here from the highest point and dropping down to the lowest point, that slopes becomes even greater. So it means that the acceleration of your cone has to be even faster. Now, if we have a typical low sensitivity speaker mated to a tube amplifier, that will make that high frequency acceleration impossible. So when you are cranking your amp up and you are forcing it to operate at or near its peak power handling capacity, then you are forcing it to make the transition between the most extreme cone and most innermost cone position, the change between that occurring at a much faster rate. And because the speaker cannot move at a fast rate, that's why we have flabby bass. So when you hear a tube amp and the bass is out of control, it's not the amp's fault, it is the incompetent demonstrator's fault who tries to put lead shoes on a dancer. So guys, this is really basic stuff that you have to know how to match amplifiers to speakers. And what I have seen in the past 20 years is that people's general knowledge level on how to match speaker and amps has just dropped down to a lot, unfortunately, a lot. So back to here, that if you have a high efficiency speaker that the cone can follow what the amp tells it, then bang, you have the bass happening. And you have the bass happening with a half a watt tube amplifier. You can have fantastic bass happening. But put that half of a tube amp with a low sensitivity speaker and you have zilch, nada, niente, nothing. So now let's see what's the situation with transistor based amplifiers, class A, class B. I don't know too much about class D, but I think that in the case of class D, the situation is even worse than class A and B situation. So here with transistor gear, we do not have second order, third order, low order harmonic distortion, which makes the wave fatter, but we have high order distortion creeping in when we are reaching near saturation levels. And it's in the order of the 13th to 19th order harmonic distortion. And that means that, for example, if you have a 100 Hertz wave, the distortion will be in the 1 to 2 kilohertz range. So that's why transistor amps typically have a clear bass, because in the bass region there's no distortion introduced to the waveform. However, this is also the reason why solid state amps have deplorable mid-range and top end, because all of the distortion starts to show up from the mid-range on and goes up to the ultrasonic region. So for example, for a 20 kilohertz sound wave, when it starts to reach saturation, you have up to half a megahertz distortion peaks riding in your signal. So this is here what I show you. This is how solid state distortion may start to look like, that you have like a nice sine wave, and instead of the sine wave it starts to get like peaky, like here, like shh. So you have these peaks starting to show up and riding on your waves. So basically, if we want to see a picture analogy, it is like when we have a transistor amp and we use a quiet signal, we have a tiny taper, we have a medium signal, we have a bigger taper, and when you reach a level where you are really pushing it, then your taper disappears and becomes a porcupine. It starts to grow spikes. It doesn't become fatter, it keeps the same proportions as the medium taper, but it starts to grow these crazy spikes. And that's why it depends on your hearing how you perceive the amps, because there's no change in the proportions. That's why people whose hearing is focused towards the bass region, they think that everything is okay because the waveform is not affected in the bass. But if you have good high frequency hearing, then you will start hearing that insane nastiness that creeps up in the sound with these transient distortions. And that's why today, so that's how people and manufacturers try to combat this situation, that they're throwing at us these amps which has monstrously high power output, like 1,000 watts, 2,000, 5,000, 20 kilowatt amplifiers, and the rationale behind those amps is that they want to stay very far away from that region where the quills starts to appear and makes the sound harsh and nasty. And you would be surprised. I'm going to show you some numbers that I calculated with my listening to the Michael E amp, is that it's just staggering how much power reserve you need in the case of a solid state amp to stay clear of this porcupine region when you have high energy transients in your music, such as like the female vocal, like Emma Kirby singing in a church, that has tremendous high energy transients, or like a sitar, it also has tremendous high energy transients. And you will notice that even if your amp is quite high power enough, you have to stay in the almost like a whisper soft zone to avoid getting these porcupine quills. So now let's have a look at a concrete example for power rating. And let's say you read a brochure and it says it's rated at 50 watts at 0.1% total harmonic distortion. And here I show this, like this is the 50 watt level with this dotted blue line, and the dark blue, it shows here that 1 amp which is rated at 50 watts 0.1%, and the green one here shows another amp which was rated at the exact same watt. And here I show you what happens if you crank the volume higher and higher. So what happens when your amp starts to distort, because that 50 watt rating, it tells you that when we have increased the signal here to a 50 watt output level, then we have 0.1% difference. So that's how our expectations and the reality starts to be different. So they have a 0.1% difference. But it doesn't tell you that if you start pushing your equipment more, what's going to happen. Because in case of one amplifier, maybe you are going to crap it out very close to it. Maybe at 55 watts, you are already entering gross distortion. And you have another amplifier, and you can push it maybe, let's say, to 100 watt, and then you reach that level. So even though both of these amps are specified at 50, one of them can go maybe just to 55 and the other can go to 100. And you do not learn that from the 50 watt 0.1% rating. You would need to see the entire curve from that manufacturer to specify how it looks like when you push it to more than that range. And here I show you another example, like a 30 watt rated amp with a super minimal harmonic distortion, like a 0.01%. And this amp can be the exact same amp as any of the other two amps, because we are specifying it at 30 watt level, which is around here. And here the difference between the expected output and actual output, it shows up as a 0.01% distortion. And when you push the amp more than at 50 watt, it becomes 0.1, and then it becomes bigger and bigger. So when you read that there's a wonderful amp that has this extremely low distortion, it just means that they specified it at a lower power level. You get that amp which is maybe specified at 50 watts at 1% distortion. Look at it at 5 watt, and you will see that it has 0.01% THD at that level. So eventually, when you look at really high power amplifier like a D'Agostino amp, and they say that okay, this puts out a kilowatt at 0.1% THD, it means that that amp will be still comfy playing at 2 kilowatts, because then it will have maybe like 0.5% THD, but it's not keeling over yet. And if they would have specified like 1 kilowatt at 1%, it really means that you are already pushing your amp to the point where it's not just ready to let go. So a single power value, power rating doesn't tell you much, and this is why you have that situation that you have an amp that's rated at 50 watts, and it has bigger reserves than another amp which is rated at 100 watts or maybe even 200 watts. And it's just that it has a nicer characteristics. It can hold its performance to a much wider range, much longer range. It's just that they specified the output at a certain harmonic distortion level, and that's what you get. But that ability of exactly how much punch your amp has, how much bass it has, dynamics, transparency, it has very little to do with this. It has much more to do with your power supply, your circuitry, the quality of the components in your amplifier, and all of these are lots of details, and it cannot be just described by a single number. So another interesting thing when you think about a trivia, that when you think about distortion, is if you have a tube amp that is rated at, let's say, 50 watt output and has 0.1% THD, that THD will be much less noticeable than the same amount of THD rated at the same power output from a solid state amp, because with the solid state, that THD is going to show up as high order harmonics, and that's super nasty. And that exact same amount of low order harmonics, it's really hard to tell, and you have to really just sit like, use your golden ear. Can I hear it? Maybe I can, maybe I don't. There's some people who can say it with 100% accuracy whether it's there or not. So it's a fact. It is there and you can hear it. I'm not doubting that. However, if you have 100 people listen to it, there are 1 or 2 golden ears who can spot it out and tell, yeah, that's going on, but 99 will be totally happy and they say that no distortion is happening, this is great music. But try the same thing with a solid state amp, and basically 99 out of the 100 will instantly spot that something is really messed up, and that one person who can't hear it is the one who has the hearing aid. So maybe this I will go into at next session, because we are already really long into this. But why this is so important is because you think that 50 watts is a lot, 100 watts is a lot. It's not much. And it's not much because when people think that you are listening to music, let's say you are listening to a 50 dB average output level, which is like a soft speaking level, which is quiet music listening, and you listen to a violin or a sitar at 50 dB, then these instruments will have an extra 40-50 dB plus transients riding in that music. And your average volume will average out to 50 dB, but they were 90 dB peaks, like microsecond peaks embedded into that music. And those microsecond peaks will really excite the distortion characteristics of your amplifier. So if you have a tube amp, it will mean that it will force the cone to move a little faster, and that will create the impression that the instrument is bigger, and has a more powerful sound. But if you have a transistor equipment, then it will introduce high frequency distortion harshness, which will make the image start to fall apart at the high frequency. So instead of a single sitar, you will start to hear as if there are 2 or 3 players in the room, and then when they pluck the string, the plucking will not appear as a strong pluck, but it will plateau at a certain level. So when you factor in this, like how an amp can truly accurately portray an instrument, then the power demands are totally different from that scenario when you are just feeding a sine wave and Dumb and Dumber situation and see like how loud we can go, how fast we can go on that scooter. And in this situation, when you compare the amps, when you compare tube amplifiers and solid state amplifiers, there's a massive difference between how much the watts count. And here we have to use fairness. So like to add, to be fair to all of the amplifiers, we have to use speakers that treat all of them well. And so let's use 100 dB efficient speakers and add it to all of the amps. So it means that basically we are comparing them with the same speaker. So there's no and there's no handicapping, because when you add the low sensitivity speaker, you handicap all of the tube amps. So if you are into handicapped racing, then okay, follow those reviews who put LED boots on tube amps and give you totally junk reviews, because it's kind of like, I don't know, whatever. But let's go back to the soil of reality and hook up 4 different amplifiers to a speaker that can accurately follow the movements, the cone movements that the amp dictates. So for a single-ended tube amp that puts out 1 watt of output power, to have a push-pull tube amplifier with the same distortion characteristics, you have to increase the power rating by a factor of 10. So a 10 watt power push-pull amp has the same transient handling ability as a 1 watt tube amp. And when you compare it to solid state amplifiers, if we look at the class A solid state amp, you need at least 50 watts to compare to a 1 watt single-ended amplifier. And even that 50 watt cannot handle the high energy transients as much as a 1 watt single-ended tube amp. And I did this exact comparison in my system with the 1 watt single-ended amp. With the sitar, it can just deliver the sitar's transients with lightning accuracy, and it like really plugs out like a real sitar string being plugged. And the 50 watt Michael Yee, when that string is plugged, it locks it to a certain volume, and it cannot go beyond that. It cannot reach the speed that the 1 watt amp makes the speaker cone do. And when you go to a class B tube amplifier, solid state amplifier, you need at least 200 watts to get into the ballpark where a 1 watt single-ended amp plays. But I have to tell you that not just any 1 watt amp. It has to be a tube amp that is properly built, and it has a power supply that is capable to feed these high energy transients. And sadly, I have to tell you that all of the commercial tube amps that you can get, I haven't found any of them that really have this type of power supply that can feed that sort of energy at a 1 watt level. However, there are fantastic amps, like for example, look at the Yamamoto. It's like 2.5 watts. Now that's much more than 1 watt, but at least that one already has a power supply that can feed energy at that speed and that level. So if you have a Yamamoto amp with a great speakers, like for example Bruce Edgar's Edgar horns, and then you try it a-bit with a 200 watt transistor amp, it will eat the transistor amp for breakfast anytime, any day. Of course, the 200 watt amp, you can crank it out and play louder, but it will just burn out your ears. So if you want to burn out your hearing, fine, no problem. Solid state amps win every time, like 100 times out of 100 they can play louder. There's no question about it. But what we are talking about, this is audio, we are audiophiles, is quality music. I want to listen to the beauties of that instrument, and I just don't want like eat a million hamburgers type of situation when you are not into quality, just into quantity. Yes, if you are into quantity, just get the highest wattage amplifier, who cares? But if you need quality, then that even 1 watt solution will give you the best quality you can find. And how is that possible? How can 1 watt be more than 200 watts or a kilowatt? We'll look at it in the next episode. And if you are curious about that, you can comment, but I think I will not reply to those comments yet, but I will reply to it with a video. Why 1 watt gives you higher resolution, higher micro detail level than 1,000 watts. So I hope you learned something of it, and now you know that when you read a power factor specification, it doesn't tell you how too much about an amplifier, but it tells you just something. And when you look at the power factor, also look at what sort of amplifier is that power rating directed at, and then you will know much more about your amp. So for example, if it's a class B solid state amp and it's rated at 100 watts, it will not be sufficient for quality music listening. If it's a same type of configuration but it's rated for 2 kilowatts, then yes, probably you will be happy with it. Or if it's rated maybe at 5 watts only, but if it's a single-ended amplifier, and you can see that they have big transformers, they did not steal the money out of it. It's not a budget product, but a well-built product. Even if it's just 5 watts, it will give you a tremendous transient response. So if you like, please like and subscribe so others can learn. Bye bye.